Yeah, go ahead.
Cool. Okay, so yeah, we good to go?
Yeah.
Right. So this part of the talk is just going to be a bit of a hands-on kind of a practical look at actually applying nested sampling in the materials context. It'll be great to get you to work with an actual kind of atomic system where we get to move around all the atoms and look at what crystal structures form out of that. However, we don't have several hours to wait for those calculations to finish. So we're going to stick with a simple example, which is the 1D Ising model, or Ising model. And I believe by this point, is there anybody here that doesn't understand the Ising model and would like me to give a recap? So we're good. Okay, all right. So I will still go through it, but I won't, kind of give it too much. I won't linger on it too much. Cool. Is it really? It's quite slow, right? Yeah. Okay. Well, so yeah, in this case, we are considering a 1D chain of spins, and these spins can take a value of plus or minus 1, i.e. pointing up or down, and it's going to be it's a finite size system with periodic boundary conditions. So just yeah, it's a chain that's been connected at each side so that your nth spin is neighboring your first spin, and each of these spins is going to interact with through exchange coupling, such that each spin can raise or lower the total energy of the system depending on how it aligns with its nearest neighbors. And we represent that with this Hamiltonian of minus j over the sums of pairs of your spin objects of your vectors, which can either be plus or minus 1. And in a sort of magnetic context, which I'll kind of come back to later when I start to talk about magnetic nested sampling, having j greater than 0 suggests that the spins will save energy by aligning with one another, which will ultimately lead to ferromagnetism, where all our spins are aligned. And if j is less than 0, then they will save energy by anti-aligning with one another, which means that they're trying to get to some sort of anti-ferromagnetic state where there's where the spins are alternating up and down. But as Manon pointed out in her talk, there are examples of more complex systems with examples of frustration where there's no easy way of resolving the kind of different there's no easy way of arranging the spins in such a way that you save the most amount of energy, and there are many different possibilities. So yeah, in the order parameter is just going to be the magnetization, which is the sum over all of the individual spins divided by the total number of spins. And ultimately, with nested sampling, we're just going to be in this demonstration, we're just going to be aiming to sample the different possible configurations in the way that Livia sort of it described in detail, and to ultimately integrate over these different possible configurations and provide an overall average ensemble energy or free energy and a total magnetization. And the key part here is that we're going to be ultimately performing this at different temperatures. However, that comes after the sampling has completed. So this goes back to what Livia was sort of alluding to, which is that this sampling is agnostic of temperature and energy. We're not, when we generate new configurations, we don't care about what the energy of that configuration is at that point in order to inform the Monte Carlo moves or to inform the updates. There is also no energy. There's no sort of Boltzmann distribution in the generation of new configurations. So even though we are sampling through configurations that can be related in some sense to a temperature, ultimately the actual sampling process is agnostic of temperature. And it's only after the fact that we've generated all of these configurations and know how they contribute to the overall phase space that how they contribute to the ensemble that we infer a temperature, and we can basically say, okay, we want to find the ensemble average for T equals 100, and we just perform a sum over all of the saved configurations for using the Boltzmann distribution, and produce a thermal average. So I'm just going to take you through the notebook that I've written. I'd like to really say that I would absolutely. This is such a simple example. I would really, if you're interested in nested sampling, I would use this notebook and Livia's as a jumping off point to kind of try some of your own ideas. And so we just start out with just a function for calculating the energy of a given configuration. We have a function for finding the of a set of configurations, finding the one with the greatest energy, which is, this is just basic, kind of Python NumPy commands and such. And then we come to how we decorrelate our samples. So as Livia said, because we can't reliably we can't use rejection sampling and just generate an entirely new random configuration in spaces that are highly dimensional. So what we do is to clone another Walker from the set. We record our highest energy Walker and record its data. We discard it and replace it with a clone of another random Walker, and then we perform a number of random steps to decorrelate it from its parent. And I want to emphasize that this makes up the vast majority of the computing time for nested sampling, is to ultimately perform all of these steps. So really, a lot of our motivation is, or a decent amount of our motivation is to kind of find new, more efficient ways of generating new decorrelated samples, with the challenge being that you can't rely on an overall temperature or energy in order to do so, because we have to remain temperature agnostic. So some way of taking a sample, and rather than having to go through all the individual steps to get to a new decorrelated sample, if there's some information that could be gained as to how to get to a new sample that is reliably decorrelated in fewer steps and more efficiently, then that will hopefully massively improve the efficiency of nested sampling. So this is just showing that process. We've saved the data of the initial Walker. We choose a Walker at random to clone, and then just record this initial energy, because it's going to be initial energy. That's important for that's important for some reason. Here's just some verbosity stuff, and so we update the configuration by taking a single spin and flipping it. And if that flip pushes the energy above that initial energy maximum that we recorded, we reject that move completely with 100%. And if so, we just flip it back and return to the configuration beforehand, and we move on and we try to flip another random spin. And we repeat this a certain number of steps until ultimately we get to a decorrelated sample. Yeah.
You say that is the temperature agnostic, that whatever is the temperature, a move toward lower energy will still be a move.
Yes. Yeah. The only restriction is that no step can take you above that initial energy maximum. Yeah.
Am I right in understanding that you're exploring just the landscape view?
Yes.
Yeah, somehow storing these configurations, and then at the end you choose some beta, for example, and then for each of those configurations you add a Boltzmann weight, minus beta EI.
Yeah.
Okay, and then you have the type of estimate.
Yeah, that's it. So we're sampling. We're not sampling from the Boltzmann distribution. The Boltzmann distribution comes in after the fact.
What if you wanted to? What's interesting is in estimating some quantity that you can't.
No, not necessarily. So once you've got your set of configurations, ultimately the ensemble average that you're going to be, you know how you're performing your ensemble average. So as long as you can calculate a quantity of a given configuration, you know how to calculate the average of that quantity. So I guess it'd be relevant to say, for example, yeah, some type of spin correlation function as a which actually I'll be showing later. If you can calculate the spin correlation for a given configuration, or in fact any quantity you can calculate for a given configuration, whether that's a vector or a tensor or anything, then you can ultimately calculate a thermal average of that quantity for the whole system at that temperature. And this is, in case I forget to bring it up later, this kind of speaks to, I think, one of the advantages of nested sampling that is kind of underrated in terms of efficiency and transferability, is that I can take, and I have taken data that I've generated using nested sampling, having a configuration and a whole array of atomic configurations, and I can store metadata in that such that I can hand it to somebody and go, what quantities can you calculate with this configuration? And if you can calculate something clever, like some clever order parameter, something that gives us more insight into the system, then we know exactly how to calculate the thermal average of that and look at how it changes as a function of temperature. Yeah, and you don't have to rerun the simulations. That's the point. Yeah.
The configurations you're throwing away.
Yeah.
Are you storing them?
Yes, those are the ones that the ones that are thrown away are thrown into those are the ones that we save. They don't go. No. The ones that go in the bin. The ones that go in the bin are the intermediate steps to decorrelate. This is the expensive part of nested sampling, is to decorrelate our one configuration and get to a new one. We have to go through a path of calculating the energies of many configurations, and it's those ones that are discarded. But we ultimately we have a set that we can save and recalculate thermal averages afterwards. Okay, so if there are any more questions? So I mean that's it. That's the premise. It's not it's not that complicated. Quite elegant and easy to code as well. I'm a physicist. I code like a physicist, and even I can figure this out. So here we have this runs that part was just the process for decorrelating a given configuration, and now this nested sampling function will start off. I didn't actually explain the whole thing. So it starts off by randomly generating. We have a certain number of walkers. We input. Well, for one, we need to first say how big our system is. So let's say we want 50 spins. Then we want to choose a number of walkers that we're going to be sampling with. Essentially, the number of walkers that you choose is analogous with the resolution. The higher number of walkers you choose, the higher the resolution of your sampling. It's going to take longer, but ultimately your thermal averages will be more accurate. And then we also want to choose how many iterations until we stop. So this goes back to the what we were talking about of stopping conditions. Practically, when it comes to using nested sampling in materials, we will kind of have an upper bound of a number of steps and let it run for a certain amount of time. And if we ultimately get to an energy that is comparable to that of a let me rephrase this. There's something slightly more clever you can do, which is for your set of configurations that you've saved, you can determine based on the energy versus temperature, the free energy versus temperature plot that you determine, you can take the energy of a given configuration and determine a most likely temperature, or actually it's not even most likely temperature, but determine a sort of a representative temperature for that configuration. So if you were to go back and do this after you've completed a run, then you can kind of determine, okay, I've gotten down to a temperature of say about 20 Kelvin, and that's fine. We don't want to go any further below 20 Kelvin. But yeah, so but otherwise the number of iterations in this case is just a fixed number that we choose, and we hope to. I can show how you need to make sure you're getting enough to get down to the energies that you require. N step is just the number of steps involved in the decorrelation process, how many random steps we're taking on the walk, and then N record is just the number of how many full configurations are you saving. You could save each configuration from each step, but practically when you're doing this with, so for example, I've just recently been doing it with a system of 2,000 atoms, and we want to save the XYZ file for each of those 2,000 atom configurations. And if we were to save it for every single step, I would end up with hundreds of gigabytes worth of data, which is all useful data, but my computer can't store it. So instead, you just sort of record a certain, you only actually record the full information, the full configuration for every n steps, every n record steps. And yeah, so yep, that's fine. Yes. Oh yeah, sorry. So n step is the number of steps inside a given iteration. So at a nested sampling iteration, you have to generate a new walker and decorrelate a cloned one. So the number of steps there is how many random steps you take on your walk to decorrelate. So in this case, in the easing 1D easing example, it will be, in this case, it will be 100 times that you pick a random spin and flip it to decorrelate your sample. And record, basically. Ultimately, it will be recording the energy and magnetization of every single nested sampling iteration, but I choose to, as just a demonstration, even though it really doesn't take that much data in this case, I can choose to only record the full configuration of spins every 100 iterations. So we always start off by generating a number of random configurations equal to the number of walkers, and then we go through the nested sampling process as detailed by Livia, where we choose the highest energy configuration and record its data, walk it away, decorrelate. Oh, sorry, record its data, replace it with a clone, decorrelate it, and you can see here that I'm kind of saving some metadata for the configuration. So this has the full spin configuration of up and down spins. I'm recording the iteration at which it was formed, because that's going to inform how you do the thermal average later. The energy of that configuration, obviously very important, because that's going to go in the Boltzmann factor. And then the magnetization is an example of a quantity that we can calculate for that given. That's one of our order parameters. But again, there's no reason. So I'm recording this now, but I could go back later and go through all of these configurations and record new data. So I've come up with this nice new correlation function that I'd like to calculate, or I've come up with some way of determining what the interplanar distance between graphite layers is, and so I can go back and just calculate that without having to do the run again. And this is the step at which we're performing the spin flips, and we've generated our new sample. In this particular case, if you don't generate a new sample, if you haven't made any changes if you haven't made any changes to the system then it will reject. No, that's not. Sorry, ignore what I just said. There's another version of this where I maybe should have showed it as an example, but as opposed to performing this walk, you could do rejection sampling, but you see that in this case, as you go to higher dimensions, it just becomes very impractical to try and generate lower energy samples completely randomly, and it very quickly begins to fail. So now here comes this is the post-analysis part. We've performed our nested sampling, and we've got our configurations and our data, our list of energies and our list of magnetizations, and this is where we just perform the integral. And here's where you have our k over k plus 1 to the power of the number of iterations minus 1, and so on here. And we just take the difference between them. We have some scaling factor here of chi, which basically takes the fact that these phase space volumes are, in the materials context, when you just calculate them as is, are absurdly small numbers. So it doesn't change any of the integrating or any of the results to just multiply them by some sort of arbitrary factor. And yeah, then we just perform the sums. These are the numerators where we just summed over the data of the different configurations. I'm gonna get to why I have a mag and an abs mag. That's absolute magnetization in a sec. And then I think to demonstrate this is so this now is demonstrating practically what we do in material, or kind of what our general sort of workflow is that we will always begin by performing multiple runs in parallel. We'll run it multiple times. We'll run nested sampling multiple times and compare their calculations of the thermal averages, and in order to assess the convergence. And so I've just set this up to allow you to run as many runs as you want and to plot them all at once. And then this one's just for analyzing multiple runs, and then it'll plot them for you. So these will just plot individual energies. And okay, so we get to actually running it now. So let's start off by choosing 5 spins and 20 walkers, 65 iterations. It's a weirdly specific number, but you might see why. And we're going to choose 20 steps. So our sort of general rule for the number of steps is that it should be at least equal. I mean, in our materials context, it should be at least equal to. It's generally equal to the dimensionality of the problem multiplied by 3-ish. But this is highly dependent on the system. You ultimately want to assess the convergence with respect to the number of steps, i.e., the number of steps in the walk, and the number of walkers. Those are the 2 main things. In this case, we're also going to have to be wary of the number of spins as well, because that's going to give us different results. So let's go. I guess I should have been running these as I went along, but run.
Good.
Yeah.
The whole configuration when you were walking, the location.
We store the energy every time. Although that's not actually that's not technically necessary. You can skip through some of them, but no. We in this case we record every energy, every magnetization, every order parameter, and we only save the configuration every n record steps. That as a memory saving sort of exercise. Why do you sometimes keep it? Because you want to be able to determine. So you kind of want a database that's going to let you determine new aspects or new properties of the system.
Yeah.
Yeah. So it depends on. So we might just be, we technically don't need to save any of the configurations if we're just interested in looking at the heat capacity as a function of temperature, or the volume, all of this stuff. But if we are interested in going back and doing some more in-depth analysis of the configurations, then yeah, we want to save the whole configuration. But we can't do that for every step, because that would involve an XYZ file of it's huge. Yeah, so in a recent example, I'm looking at alloy systems that are made up of about 2,000 atoms, and I ultimately restrict the number of configurations in the file that we're going to share as part of the paper to 1,000, just like a nice round number, because you can always just sort of lop off some of the configurations you've saved after the fact.
If I understand correctly,
Yeah, no, that's fine.
Say like later on, I've got this new function that I
Yeah. Yeah.
But it's quite a complex function. You need the particle.
Yeah. Yeah.
You then thin your nested sample and only take those samples that have all of that extra information.
It would depend on whether it would depend on whether that's you do that. So you as part of the PyMatNest package, there is an input that's equivalent to nRecord, which is the number of times it will print a new trajectory to a trajectory file. So you can have that. You can always save that data and perform the integrals with that. The key thing to point out, I think what you might be getting to is that you do have far fewer points in your sum than you do for the energies, for example. Like for the energies, you might be summing over 1 million energies, but for the if you're performing an integral for some other quantity like radial density functions or some kind of spin correlation, you're necessarily going to be using fewer. However, we find that you only need a fraction of that total number to get good integrals. Yeah, because it's still you're doing a sort of an even sampling, but still you're still capturing, for example, the phase transition. The sampling of the phase transitions is more dense, so you're still going to be picking up on those more dense regions anyway. And it turns out it works nicely. Yeah, it ultimately depends. You always have to check when you're saving, based on the amount of data you're saving, whether you're still achieving convergence. So if you've done multiple runs and you check your thermal averages, you have to make sure that there's still good convergence for the reduced set.
Basically, you said that the greatest part of the computation cost is when you try to simulate new configuration that is decorrelated.
Mm-hmm. Yeah.
But have you ever tried the few numbers there, so that it's not totally correlated, but there's still some kind of correlation.
Mm-hmm.
And I think you don't have to really.
You're just talking about reducing the overall number of steps. But that will you're basically inducing, because you're always picking from the walkers that already exist inside a set. You're essentially imposing correlations in the data that you don't want, because you want at each iteration you want the configurations to be equally distributed in phase space. So you don't want to have a walker. So you've got your walker that you've recorded, and you've cloned this other walker. You then don't want to do few enough steps that you only get away a tiny amount, because then these two samples will be highly correlated. Hmm. Yeah, I see what you're getting at. I don't know, Livia, do you have a better response than I do? It just ultimately it doesn't work, right? I mean, you practically, as someone who just largely applies this, I know it doesn't work, but I don't have a. Because remember, this process, ideally, we would have some magical way of just taking our walker and just generating a new one that is representative of the equal distribution of the walkers that are inside the that are below that maximum energy. The way we get to that is through a random walk. If you were to, I guess if you were to keep doing that, then there's a if you were to have a very few steps, think of it this way: you take your walker, it's cloned, you only walk it a tiny bit away, and then you ultimately choose another walker. It's then going to become more likely that you've cloned the same walker and only walk a certain and only walk a little distance away in phase space away from it, and you'll have a cluster of points that I guess might all move in tandem through the system, but it's not. No, I don't know. It's, yeah. Okay, so just to emphasize, I've separated these steps to emphasize that we can run the nested sampling, and run it, and it's very quick because we've chosen a small system and a small number of walkers, and now we've stored this information with which we can perform the analysis. And as I've spoiled from the fact that I've already run this before, this should be fairly poor result. You know what? It ran. Sometimes at this case where you've got only 5 spins and you're using this specific number of walkers, then you get very highly variable results. So actually, I'm just gonna keep running this. So sorry, I should add context. So we are looking at in black the exact solution to the 1D Ising model of the free energy as a function of temperature, just some kind of scaled quantity that's related to temperature. Then that's in black, and we're obviously we're trying to get good agreement with that. But this is pretty good. It's better than the last one you looked at. But let's try it again. There you go. That's more the type of thing I was looking for. See, in this case, in our 3 separate runs, 2 of them, the orange and the green, have managed to iterate their way down to the lowest energy we would expect, which is -1. It just so happens that one of these runs, because we didn't use enough iterations, only managed to get to a minimum energy of -2. So it's not adequate. You can see it plateaus at -2, and it's a highly sort of degenerate system. So yeah, that happened to happen with that one particular run. So what we would want to do in this case is to just increase. We could try increasing the number of steps. Number of iterations. They can be quite. They're all quite similar sort of things. So easy to confuse them. Let's try that again. So we're now allowing for more nested sampling iterations, and okay, they've each managed to get to the lowest. So as far as we would say that this has done a pretty good job of optimizing the energy, in that each run has managed to get to the lowest energy, but overall the integral is just not sufficiently. It's not sufficiently calculated.
Again, what is the x-axis here?
Oh, it's temperature. So we recalculate at given temperatures, which we've just. So we've input we recalculate these thermal averages for a range of temperatures, which we just choose. Yeah. Oh, it is a temperature. Oh, no, it is a temperature. It's not like Kelvin or degrees centigrade, but it is. Yeah. Sorry. But it's a scaled temperature. yeah, so I would look at this and go, okay, we've got enough steps, but the actual convergence on the real result is rubbish. So typically you would then go back and increase the number of walkers. Let's try 40. And see, oh, actually, okay. So, I'm gonna ask the audience. Can anybody guess what's happened here? We've increased the number of walkers, but I didn't change anything else. So why? There's decent convergence between the three curves, but they've all plateaued at basically the same point, which is way higher in energy than the minimum we want to get to. Michael's thinking very hard, but we've increased the number of walkers, i.e. the resolution, which means at the same time we would expect there to be required more iterations to get to the minimum energy. Basically, it kind of scales as the number of walkers. So the number of steps required to get to that minimum energy scales about the same as the number of walkers you use. Oh, no. I don't know, Livia. You know, you're more familiar with the background. Has anybody actually? Yeah.
No, yeah,
Oh no. Oh, there almost certainly is a theorem. Don't ask me. I'm not some kind of nested sampling expert. Come on, why would you expect me to know that? But there are actual theorems for this stuff, I believe. Livia, help me. Okay, there you go.
Probably depends on the dimension, right? It depends on the volume filled by the particles.
Or no, what you're spacing in that closer together, right? So you can have more steps to get to the
I think
Yeah. That's a bit of sort of homework for everyone and for me. Okay, so in this case, we want to go back and increase the number of steps. Sorry, not the number of steps, the number of iterations. Dang it. Let's try. So we doubled the number of walkers. So let's try doubling the number of iterations. Notice it took a tiny bit longer that time. Pretty good. All right, but no, I think we're going to have to increase the number of walkers by quite a bit. So, by the way, sometimes this will give you results that seem very well converged, but it seems to be the random outcome in this particular system. Usually, if you do it on a large number of atoms in an actual atomistic system, then when you see convergence, it's actually convincing based on 3 runs. But yeah, let's try just going up to 100 and increasing the number of iterations to, what was it, 800? Well, nice round number of 1,000. Oh, that's a good point. I would approach this basically just from a I would try both at the same time personally, but thank you for reminding me that that's something I need to do.
Have to have sampling that enough in the smaller volume as well. Converging with the number of Monte Carlo steps, that's whether you're able to fulfill the uniformity criteria or not. And that's much more complicated to be able to estimate, because you mentioned sometimes the space can have really weird, narrow pathways that you have to somehow propagate along these as well. But if the landscape is not very complicated, you want to see that increasing the number of walkers or increasing the number of decorrelation or the number of steps it achieves the same kind of convergence. Once you're over the threshold, that you convergence.
Okay.
I think this would work very well with about 5 steps instead of 10.
You're suggesting I use 5 steps. Okay. Let's see. Oh, it's still, okay, hold on, it still works. But you know what, actually, let's increase this. Let's do like 15 runs and see how this looks.
Intuition, or more than intuition, work.
You know what? That's actually surprisingly not that bad. I'd say I would have expected that to be worse. Okay, I think okay, but is there okay? This might work. Okay, right, fine. So this will work in the case of 1D Ising. I totally see what you're getting at now. Yes. Yeah. That's interesting. I'm learning something new. Thank you, guys. This is great. I mean, we're not. I mean, no. Currently, we're not. But I mean, there's at least somewhat decent convergence between. There's better convergence between the curves than.
But with the curve in the.
Yes. Oh yeah. Oh yeah. Yeah. Sorry. Yeah. Yeah. Yeah.
What was that?
The black line is the theoretical result for the algebra for each number of states, but we have just 5 states. So we represent the whole one the algebra with 5 states.
Yeah.
Okay. Just for fun, I'm doing one step, but yeah, I feel like just keeping it at 5 spins for now. And we do need to finish up in a sec because we do actually have more things to present, and it's getting close to 5 o'clock. Well, look, but I think this is it's representing. Okay, yeah. Huh. This is it. I want. This must be this. I mean, this is. Yeah.
Having one plate swap is enough to keep it kind of roughly correlated in these people.
Okay, so let's push it a little bit. So we've increased to 20 spins. Let's go with 2,000 walkers, and this might be. Yeah. I'm not going to do 15 runs this time. Yeah, let's stick with 3. Sorry. Okay, all right, fine. 5 steps. But this goes to show I set this up as a demonstration, and it's just fun. It's fun to play with. Interesting. So better. So the runs haven't complete, which means we need to shove it up. But yeah, let's just be safe. This is going to take a little while, but in the meantime, how's everybody's week been? we enjoying ourselves? Yeah. Let this go. Are there any questions while this is going? And then this will be the last thing I do. I think this is kind of demonstrate. I don't know. It's giving a bit more intuition, certainly for me, for kind of how this works. Yeah, but no questions for now.
Other quantities.
Oh yeah.
To show. I see on the static version that there are no thermal.
No. This is me being slightly naughty, I guess.
But there are. It's just there would be thermodynamics.
Yes. Well, yeah. So this, as far as the 1D Ising model goes, this. So if we try to calculate the average magnetization in this case, then nested sampling is just going to take all of the configurations that have been generated, and you've because it's top down, you don't have the issue of what is it, critical slowing down, because you're coming down over the phase transitions. So you're sampling both the polarized cases of fully up and fully down at the same time, but because we're talking about a highly degenerate system of a small number of spins, we have to incur a random number to the energy to distinguish between degenerate states, and that kind of in this kind of very specific low dimensional highly degenerate case starts to introduce some issues where it's simultaneously sampling the majority up and majority down states, such that there's some kind of fluctuation between up and down at lower temperatures, which isn't reflected. You would just expect the average magnetization to be zero across the whole. For zero external field, the magnetization should just be zero the whole time. I think we're done now with these calculations. Let's hope for something nice, and then we'll move. Oh, look at that. That's pretty good. Yeah. Thank you. Clap me. And okay, yeah. So this is if I were to normalize the magnetization for each in each case, and only take the total magnetization normalized, then we do have a quite a clear sort of phase transition from paramagnetic to ferromagnetic. But when we just look at when you don't make it the absolute magnetizations. Oh, I might have actually written that slightly. This should be, apologies. This should be just the magnetization. Ignore the actual thing written that has the absolute the bars. Yeah, you see that there's obvious deviation in different runs, even though we've converged the total energy and the absolute magnetization. The magnetization, the average magnetization overall is works less well. And this is, this is an issue of sort of having a low dimensional system, I believe anyway. Okay, so yeah, that's it. I hope this has helps with an intuition of nested sampling, and yeah, it certainly helps me. So I think now, Livia, you're tagging in. No. Oh. Okay. Cool. So, okay. So now I'm just kind of wanted to give you an insight into what I do with this. So I'm aware that as I've very thoroughly demonstrated here, there is a lot of stuff that I'm not coming from a strictly statistics background or a mathematical background, so my knowledge of this stuff is somewhat limited. My background is in condensed matter magnetism, so I'm coming at this as somebody who's keen to take advantage of nested sampling to look at actual real systems of real magnetic systems. So with that. I hope this convinces you to care a little bit about magnets. Feel free not to listen to me if it doesn't. So this is what I've done as an expansion of Livia's work. So first off, just a brief introduction to magnetism and why we should care about it. How we incorporate the magnetic atoms into the nested sampling algorithm, which turns out was quite elegant. And then testing the accuracy of nested sampling against Monte Carlo, though you've seen actually in that demonstration that it performs integrals pretty well if you use the right number the right hyperparameters. And looking at it from the perspective of some novel fixed lattice magnetic systems, so just keeping the atoms on lattice in a fixed way, and then what happens when we kind of break away from the lattice, and well, I'll leave that to later. So this is why we care about magnets. They're in everything. I mean, yeah, computing, audio, electric motors. Obviously, clean energy magnets are highly involved in, and ultimately, we are looking to develop new magnetic materials that don't depend on these sort of highly critical, very expensive, hard to come by, and sort of politically fraught rare earths. So rare earths are at the center of the vast majority of magnets that we use for actual applications, and yes, while they are these rare earths for having F electrons in them, basically produce very large kind of magnetic responses and have very large energy products, which means that they can actually be applied in an industry context. Usually, we will end up alloying some amount of rare earth with transition metal magnets in order to bring up the Curie temperature of the material. But still, that involves using some amount of rare earths. And we would really like to, in a lot of applications, move away from that and into what we call gap magnets, which sits somewhere in terms of performance between your very cheap, ferrites, hematite, and such, and your high performance rare earth based magnets. And there is literally a gap there. There's a huge gap where actually for a lot of applications we don't need the full performance of a rare earth magnet, but there don't really currently exist reliable ways of magnets that can reliably sit in the middle and be applied to kind of medium performance in medium performance contexts. So as a case study, there's this one possible kind of candidate as a gap magnet is iron nickel, which if you were to synthesize iron nickel in a lab just without kind of doing anything else to it, just kind of melt it and cool it down, then it forms a structure that is paramagnetic. The crystal structure that it forms is such that the system is paramagnetic. But a form of iron nickel has been observed in meteorites that have been allowed to sit. They've been sat in these meteorites and they've whizzed around the universe for millions, billions of years, which means that they've been allowed to reach thermal equilibrium and get to the true ground structure state of iron nickel, which is called tetrataenite. And that has this layered structure, which I'm showing here, where you've got layers of iron and nickel. And what that does is set up it lowers the symmetry of the system such that the overall magnetism, such that you enhance kind of key properties of the magnet. And really, a lot of effort is being put into finding a way to reliably actually synthesize the tetrataenite. And so it'd be handy for computational methods to be able to predict the structures of magnetic materials. So atomistic spin models, a lot of you are kind of familiar with these. We've got the Ising model there. And alternatively, you can go for a Heisenberg model where the spins can point in any direction. But ultimately, just as a bit of insight, sorry. In order to accurately study magnetism, you really do need to get to the electron level. So you need to be performing ab initio calculations from first principles, which include the electrons, and that is just you can do that, and there are more and more ways of doing that on large scales, but it is still a very expensive. It's a very expensive method, and particularly when you include magnetism, it becomes even harder to converge these electronic structure methods. And so people usually resort to, and are just generally interested in, as as mathematicians or physicists or chemists, they would like to kind of look at accurate approximations of magnetic material. So you don't have to take into account the electrons. You're just boiling an atom down to a point and assigning it with a spin that points in a particular direction. And yeah, when you really, these models can work pretty well. They can be informed by ab initio calculations, but this is what we kind of ultimately have to work with for the time. Well, I mean, yeah, we do have to work with it for the foreseeable future. So this is just going over the nested sampling algorithm and showing that, oh look, when you try and integrate just a basic single spin in a field, so then it does a pretty fine job. And when we compare, if we perform nested sampling on a 3D system of Heisenberg spins, then we get good agreement with Monte Carlo. And then on a 3D fixed lattice Ising system, we also get good agreement with Monte Carlo methods. Oh, sorry. What is the, sorry? Oh, yes, sorry, yeah, I should be, yeah, sorry, I should be providing more context here. So when it comes to magnets, often these materials at higher temperatures, while they appear to be non-magnetic, they are in fact paramagnetic, in that all of the spins on a macroscopic scale, all of the spins are completely randomly aligned, such that the magnetism cancels out. As you cool a magnet down, you will hit a critical temperature known as the Curie temperature, where you induce where there is enough correlation such that the magnetism, there is an overall direction of magnetism, and you've broken the symmetry of the system. And then eventually, when you cool it down to T equals 0, then you have a fully aligned, completely 100% ferromagnetic system where your order parameter, the magnetization, is equal to 1. But this Curie temperature is a first order. This phase transition is a first order phase transition. Yes, it is. I'm running low on battery. Oh well. So yeah, that was just really taking what we did with the 1D Ising and just applying it to a 3D system. This has been done to death, and it's nice to see the nested sampling works. It can integrate things, but I mean now we can try out some slightly more novel systems where, as I said, we have this exchange constant which tells us how our spins interact with their neighbors. But now, what if we were to assume that there's some variable interaction with their next nearest neighbors? And this is actually akin to how real magnetic systems behave. There are the interaction with their nearest neighbors may be described by some exchange constant. As you go further out, there'll be the exchange constant can change in size or even change sign. So this is kind of approaching something that might be akin to a more realistic system. Although just for regular iron, you can kind of get a decent enough approximation just with nearest neighbor exchange. And this is just showing showing a phase diagram where we have calculated the heat capacity of our of this particular system as a function of temperature, and we can determine where the phase transitions occur based on the peaks in the heat capacity. Which unfortunately I wasn't here for David's talk earlier, but I assume this is some of the peaks in the heat capacity corresponding to phase transitions. Okay, so you understand that a peak in the heat capacity corresponds to a phase transition. And if we fix our nearest neighbor, J, to be ferromagnetic, and then vary the next nearest neighbor over some range, then we get this is our kind of phase diagram that comes out of it, which is which I will now go into slightly more detail about. How are we doing for time? Okay, I can get through this. So when there's when the next nearest neighbor interaction is ferromagnetic or weakly antiferromagnetic, then ultimately the structure you find at t equals 0 is ferromagnetic. All the spins are aligned, and they can point in either one or two directions. I think this speaks to a potential strength of nested sampling, but as you could see in the 1D case, I think it needs more investigating, which is that, yes, it is capable of traversing. It doesn't even have to traverse the barrier in the potential energy between the fully aligned state in one direction and the ferromagnetic up state and the down state, because it's coming from the top. So it can sample both at the same time, but I think more work needs to be put into actually determining how reliably it's determining the relative phase space, the contribution to the phase space from those two opposite points. But I think as you get to larger systems where and it's also non-degenerate systems, then I think that it's less of an issue. But that's not based on much. So now we introduce we increase the antiferromagnetic coupling more. So going down on this graph, we're decreasing the exchange coupling on the next nearest neighbors and making it more antiferromagnetic. And so there's a point in this B region here where now we're finding that the ground state structure is that of what we would call it's a copper platinum structure. So we've got these nice layers of up and down spins. And it turns out that this is an exact compensation point when the next nearest neighbor interaction is equal to the nearest neighbor interaction, equal and opposite. This is a compensation point where the energy of the ferromagnetic state is equal to the energy of the antiferromagnetic state. And so you can actually, nested sampling samples these kind of combinations, this coexistence between ferro and antiferromagnetism, where it samples a fully ferromagnetic state, it samples a fully antiferromagnetic state, but it also samples slightly more complicated structures where you have layers of up, down, down, and up, down, down, down. And it's possible to show analytically that these two structures should in fact be equal in energy. Yeah.
So when you say that a sampler is able to sample all these configurations, you
yeah.
said some workers, before you had 20 workers or whatever,
yeah.
some workers will converge in the first one, and some workers in the second one,
yeah.
and they are equally distributed. Is it like the weight?
Yeah, the distribution is akin to the weights of each configuration in the average. So I can kind of in my list of saved configurations, I can go to a set of configurations that exist over a particular temperature range and look at the different configurations that exist there and say, okay, at this temperature, these structures are able to coexist with one another energetically. Okay, yeah, and this is just a very half-hearted attempt at just showing that these two structures should in fact be equal in energy. And okay, so now we're at nearest neighbor antiferromagnetic coupling and next nearest neighbor. Well, we're varying the next nearest neighbor exchange coupling from ferromagnetic to antiferromagnetic. And you can see it's there's a whole bunch of different phases, so to speak, where we have copper platinum once again when we have fully antiferromagnetic coupling. So nearest neighbor and next nearest neighbor, both antiferromagnetic up to a point. We just get back the antiferromagnetic result. If the next nearest neighbor exchange is weaker, then we get a completely different antiferromagnetic structure which I've just called AF2 because I couldn't find an analogy to it in materials. And once again, so at this compensation point, we have coexistence between these two states, and they can kind of form these nice kind of combined structures between the two. When we go up further and we make the next nearest neighbours ferromagnetic, then we now actually come back to this L10 structure, which I need to stress, I'm representing the spins here. The structure that we're looking for in iron nickel is alternating between iron and nickel. I haven't just sort of spontaneously found actual like L10 iron nickel here. It just so happens that the spins kind of resemble the same structure. And once again, more coexistence at the compensation point. And now this is a demonstration on a 2D hexagonal lattice of frustrated antiferromagnetism, where I'm demonstrating being able to, for example, calculate a spin correlation function and show that at these higher so temperature is now on the y-axis. So we can see. So this is the heat capacity here. We've got some phase transition going down in temperature. The magnetization is staying relatively low throughout. I don't even know why I plot the magnetization because it's antiferromagnetic. And what this shows from the spin correlations is that it takes we have to get to very, very low temperatures before any structure forms in the spin state. But there is a spin state that minimizes the energy, but that we have to get to very, very, very low temperatures, down to far less than a fraction of 0.1, on this arbitrary scale, before we get these peaks that represent some magnetic structure. And these peaks here correspond with this structure, and it does look kind of fairly regular, but if you notice, if you follow these lines here, then you'll actually notice that the spins are very slowly rotating along these lines, and you can pick out the same behavior going along other sort of hexagonal axes as well, which is just, I mean, this is kind of demonstrating what nested sampling can do, which is that it can ultimately find this state, and also tell us, kind of give us a temperature profile of what the correlations look like. Okay, I've got, yeah, maybe. Okay, so now this is the juiciest stuff. We now let the atom. We take the atoms off lattice and we let them go anywhere they want. So it's the same as what Livia was describing, except now those atoms are magnetic atoms. So they each have a local spin. So we've essentially increased our phase space from 3 n dimensions to 6 n dimensions. And in this case, I'm just choosing a simple Lennard-Jones potential for the atomic interactions, and this is one of the results. So now confusingly, I'm plotting the radial distribution function, which is telling you the overall structure. So as a function of the x-axis here, as you get further out, it's telling you a peak will tell you that there exists an atom at that distance. So at these higher temperatures, this is what we would say is like a liquid state, where there's a much broader distribution of atoms. And then at some point at this peak, we get a phase transition into a solid state, where the peaks are much more refined. And as we go further and further down in temperature, these peaks become more and more refined as the system locks onto a lattice. And what's interesting here is that I've set it up such that the exchange interactions should be antiferromagnetic, and we should expect some amount of frustration. But you can kind of see that frustration here at this at t equals 0.6, where it still hasn't really settled on on much of a regular structure. There are some kind of appearances of structure where we've got spins largely pointing one direction along this axis and largely pointing along one direction along here, but then there are kind of breaks in that as well. But what's really cool is that when you let the atoms move, it solves the frustration by stretching the lattice. So it stretches the lattice in exactly the right way, such that over this cutoff of 2.0 angstroms, which I've noted kind of on this RDF here, it has expelled exactly above this cutoff these atoms. So for a given atom, these four will be exactly outside of that cutoff, and these atoms will be exactly inside of it. That is how, yes, such that the system is able to find a regular magnetic structure and minimize the energy. And this is just more on a 3D system. It's another similar phase diagram where we can look at different structures. It's kind of interesting as you increase the size of the exchange parameter. At some point, it starts to mix with the kind of representative transition, the chemical atomic ordering transition, such that so at the lower exchange parameter values, we have our structural phase transition here, and we get to a lower temperature, and you can see from the color change that the system has become ferromagnetic at some lower temperature. And these are our TCs. But then as we increase the size of the exchange constant, there's mixing. There's a mixing between these transitions such that we actually get that we find that the magnetism drives a transition from a liquid that's of a lower density to a higher density before the system transitions to a solid. And at that point, the magnetism actually starts to really dictate what the atomic structure of the system is as the magnetism becomes stronger. And you know what? I mean, that's basically all of that I was saying. And that's it really. Thank you for listening to me as I went on about magnets for about 25 minutes. Yeah. Yep. Okay. This was a while ago now. I want to say that for a system, so this was 32. These results were 32 atoms, which for a Leonard-Jones potential. We would expect to use about 600 Walkers for that if it was non-magnetic. So I believe I increased the number of Walkers up to about 1,000, and the overall amount of time it took, because these are very simple interactions, just pairwise interactions, and it's a Leonard-Jones potential and just simple sort of Heisenberg interactions. The calculation must have taken only maybe about a few hours, like two or 3 hours, if I remember correctly. That is on multiple processors, though, to be fair. So that was on maybe about 20 processors. Yeah.
And if you injury the number of workers, you get 1,000 workers, 1 million or something. But the extra computational cost comes from is George explained, every iteration you need to have a random walk or some kind of decorrelation to decrease the cost by another.
Yeah.
So if it's all single domain.
Oh yeah.
Yeah.
Oh yeah.
Domain will in way with the
No. Yeah. Yeah, no. This is this is very much single domain. It's only the maximum I did was 32 atoms. I've done 64 atoms as well, but that's kind of the motivation. If we can really bring down this time it takes to decorrelate our systems, then we can maybe start to get into the larger systems with domain walls and with grain boundaries and such. Is that, by the way, is that something that you kind of actively study yourself, or because if so, we need to chat. Okay, all right. Okay, fine. Yeah. Mm. Yeah. Yeah, sure. Yeah, I think you could generalize this in a sort of a, you could scale this up to micromagnetics essentially. I think without losing the, I think it's essentially transferable to a sort of micromagnetic scale. So yeah.
Back to the physical application. Do you have a clue where could it be useful to use, like which applications could be useful to use nested sampling, which is not really popular in statistics? For example, something that comes to my mind, maybe for base factors in model selection, you could use, like you want to compute volumes and integrals, and you could use nested sampling. Do you have any experience in statistics? Like, yeah.
I think we represent the people who are saying we're looking into these sorts of frontiers of science, like developing new magnets that will go into everything that you use, and we don't know as much of the statistics as you guys, and hopefully we might be able to get help from you to get this going faster and let us look at bigger systems. We're coming from that direction. We can't really we can't help you out as much.
I think there are no.
There are people using massive.
No.
Okay. And you have to be.
Well, just on the base basis, like the stuff that we are about, like India South and collaborators in Austria, where we kind of like together.
Yeah. Makes sense that, yeah. So SMC is kind of a similar flavor to nested sampling.
Okay.
Instead of killing one particle, you just reweight the particles according to the energy, and then maybe you resample, duplicate particles, and then
That's SMC.
Yeah, SMC, sequential Monte Carlo.
Oh, okay, yeah, right.
Yeah.
Yeah.
Just like one thing to the data, factor analysis is one. So I guess kind of Bayesian averaging.
Yeah.
I mean, that's later.
And they're using nested sampling.
And a version of it.
A version, yeah. What's the name of the picture?
Like nested sampling and like sequential Monte Carlo with it.
There is a paper in Nature, right?
No. And bias and consistent sampling via sequential Monte Carlo.
Yeah, slightly different question here. What software packages are good on these guys? I know Dynasty are there, and there's software versions.
Yeah.
For a different system, we want to have a different energy function and code it out different energy functions that they work. So if I want to play around with different functions, I don't want to code them up because I want to actually code them down there. So the need to have a material information package that we use those but the other thing, the actual analysis is something that algorithm is so simple that sometimes if someone has a very simple model with the system George mentioned, where we have an error analysis and we just explore the ordering of the different atom types on the then it's just much easier to write the analysis on top of.
Okay. Definitely don't want to. We're 7 minutes past 5 now, so.
Thanks. Yeah. Oh, yeah.
Oh.
More of it. It's yeah. And then the first one. Yes. And thanks.